My name is Afan Danish. I'm team lead of Team Hard Coders from Jamia Millia Islamia, and our project is Project S.H.E.R.P.A, and my team members will demonstrate our project ahead.
Hi, I'm Mars, and I'm here to discuss the problem statement. The biggest danger at high altitude isn't just the lack of oxygen, it is that our brain lies to us about it. We face a phenomena called hypoxic anosognosia, where a climber can be critically ill yet feel confident. It is the so-called happy hypoxic effect, which happens right up till the moment of total collapse. Current technologies fail to catch this because it relies on latency. SpO2 levels are a lagging indicator. By the time it drops, it's often too late. The true precursor to cerebral edema is ataxia, the loss of motor coordination, but right now we have absolutely no way to monitor this in real time. Smartwatches fail because of the extremity problem. Tracking poles and arm swings create massive signal noise. You cannot simply and accurately measure center of mass instability from a wrist that is moving everywhere. Even if you could get the data, you hit the terrain paradox. Standard algorithms are confused by altitude. They can mistake the heavy exertion of a healthy climb for the stumbling of a dying climber. This leads to false alarms, and eventually the user ignores that device. Finally, we are in an RF denied zone. There is no cloud. We need a system that makes life saving decisions locally, on the edge with zero latency. This is the gap we are here to close.
So moving forward, now let's discuss the need for this specific approach that we took. So standard gate analysis has a fatal flaw, and that is the intensity trap. So simple algorithms mistake high energy exertions like the steep climbing for instability. Now to solve for this, we don't just track movements, we have to decouple the intensity from the coordination. For example, we need to split the signal into certain orthogonal dimensions. For example, energy for force and rhythm and balance, and create indexes out of all three. And the algorithm should detect only the change from the mean, automatically accounting for the user's natural baseline, right? Now, this is the only way to mathematically differentiate between a healthy climber working hard, who has a high energy but low sway, and a hypoxic climber who is failing, showing low energy but high sway, right? Now, talking about the terrain paradox. A stable walk on a flat ground looks mathematically distinct from a stable walk on a 30-degree incline. Now, to handle this, we should use a barometric control loop for dynamic gain scheduling, and this system identifies the terrain state and adjusts the strength of each dimension. For example, on a steep ascent, we attenuate the energy to ignore the heavy stepping noise, and on flat ground we amplify the rhythm sensitivity, right? Now let's talk about the placement. So wrist and ankle sensors suffer from the massive kinetic artifacts like the arm swing, of course. So to calculate a true stability index, we must measure the body's center of mass, and we mandate the placement at the L3 posterior vertebrae. So this also ignores the soft tissue noises like breathing and stomach movements. So in conclusion, we have to fuse orthogonal metrics and adapt to terrains, anchoring to the center of mass, and this kind of gives us a much more stable and robust system.
Taking on from Zaheb, since we aim to measure the balance, rhythm, and coordination of the mountaineer, the core logic behind this approach utilizes stochastic normalization, where instead of simple limits, we use an irregularity index to compute a coefficient of variation in mean. First, mean is calculated using a 30-second moving average of the required quantities. Second, variance is calculated by summing the squares of the difference between the instantaneous values and mean, and dividing this sum by the mean obtained in the last cycle. The irregularity index then is simply the square root of variance divided by the mean. Each irregularity index for energy, gait, and sway stability normalize signal noise against the user's current activity level. Having instantaneous values and their irregularity indexes, we calculate the acute mountain sickness score by taking the product of the quantities and their respective indices, then summing it all up to get the score. The barometric control loop identifies the user's kinetic state, ascending, descending, or flat walking. The system then dynamically reweights the indices based on the identified state, where we attenuate energy index and amplify step and sway indices. When true altitude breaches the silent hypoxia threshold, a global risk factor is applied to all sensitivity gains. We flag any anomaly in this score using a buzzer and use a proximity sensor to recalibrate the entire setup. For Team Hardcoders, thank you.